Go ahead.
Okay, thank you, Richard. Hello, everybody. So as Richard mentioned, this is a joint collaboration between Bruno Kessler and Università, Politecnica, delle Marche. And I would also like to say that we started this activity, this work, during the Generic Summer Workshop in 2019. So I would like also to thank the organizers and Maurizio Mologo for setting up the team. He could not be in the author list for some reason, but of course his help was very valuable. Okay, so the problem that we are addressing here, we want to try to do distance speech recognition in ad-hoc microphone networks. So in this application scenario, we have multiple heterogeneous microphones distributed in an environment, so have different characteristics, and also they are facing different acoustic conditions, so the SR performance varies considerably across the channels. And finding a way to properly use the information provided by the distributed network is still rather an open issue. So for example, one approach would be to try to combine the signals at the channel at the signal level, for example, using beamforming or similar approaches, or as we saw in the first presentation today, trying to do a multi-channel speech recognition system. However, in general, those systems are designed for compact microphone arrays. They require that the signals are aligned at the sample level, which is something that we don't have in an ad hoc microphone network. We can aim at some loose synchronization. And then also, they don't work very well, in my experience, when there is a huge difference between the performance of the channels. A very effective approach would be to decode all the channels and then combine the ISR hypothesis afterwards using, for example, Rover. That will probably give the best results. However, you can understand that if we have a lot of microphones, decoding all of them would be very expensive from a computational point of view. So what we try to do in this work, we try to find a way to check if it was possible to select one of the microphones, the most suitable one, and decode that one, use only that one for speech recognition. So this is interesting because, of course, it doesn't need signal alignment at sample level. It is rather cheap from a computational point of view, and also we observed experimentally. I think also in the previous paper, it was in the first paper today, it was observed something similar, that if you're able to pick the best microphone, you actually get more benefits than doing speech enhancement and combining them. So there is some literature on channel selection. Let's say the most straightforward approach would be to take the microphone closest to the source, so using a distance-based criterion. There is a bunch of works that try to estimate metrics representative of the quality of the signal, like signal-to-noise ratio, envelope variance, chapsel distance, STOI, PESCU, whatever, so that they can pick then the cleanest or the highest quality microphone. And then also there are some works that rely on evaluating the entropy of another acoustic model, different from the one used in the ASR backend, assuming that, using the entropy of the posteriors of the acoustic model allows selecting the channel, which is more informative. These approaches works reasonably well, but what we think they are missing, they are not taking into account what is that the ASR backend actually wants. And this information is typically not available, but even if you know how the ASR is designed and how it has been trained, it could be difficult to know a priori what are the best acoustic conditions. Maybe the ASR has been trained on multi-condition training, and then it would be difficult to decide between two channels which one is the best one. So what we try to do, we try to develop a fully learned channel selection approach. So we want to have a model, we give some acoustic features as input, and then we want that the model tell us an estimation of what will be the ASR performance, let's say, on that feature set. And we want to do this using the word rate given by the deployed ASR backend on some training data. So this is in our opinion, this approach has two very nice features. It doesn't need the signal alignment, as I mentioned before. It is agnostic of the geometry of the Microsoft setup, so I don't care anything about that. And it selects what the ASR prefers because in terms of acoustic condition, because we train the model based on the word rate given by that backend on some training material. So channel selection is basically, if you think about it, is basically a ranking problem because we don't care actually about the actual performance, the absolute performance of the ASR on that particular segment given by that channel. We just want to put all the channels in a rank one after the other and take the best one, or we could also take the top end and then do other combinations. So in information retrieval, there is this well-established framework, learning to rank, introduced decades ago already. And so what we wanted to do, we tried to take this framework and try to port it in our speech processing domain. Okay, so basically the mapping is the queries are our utterances, the documents that are retrieved by the queries are our channels, and the relevance scores that are used to rank the documents is basically the word error rate, or actually a metric related to the word error rate. So I skip here the mathematical details and the problem formulation. You find it in the paper, and that will be super boring. I just give you an overview of the 3 different learning to rank strategies that we investigated and then evaluated experimentally. Okay, so the first thing that we tried to do, of course, so we had the features, we had some word error rate results in the training set, so we tried to train a model that takes the features, the acoustic features as input, provide the scores, and then we use the cross entropy on the soft labels to train the model. Actually, we didn't use the word error rate because, as you can imagine, this is not a very suitable metric because it is unbounded. We tried to do some normalizations strategy whatsoever. Then, in the end, we figure out that taking the word accuracy is a good trade-off, and it is already bounded between 0 and 1, so it works fine. And so we train this model. You can train with cross entropy, or if you want, you can also train it with mean square error, so you try actually to predict the word accuracy. So this works fine as long as the model learns what it has to learn, but it has 2 limitations. The first one is that the task is more difficult than what we actually need because we just want to rank the channels. And then the second point is that it doesn't take into account the relative position between channels within the same utterance, position that may change depending on the utterances. Okay? So it doesn't do that. We just train using all the audio segments that we have. So we moved to address these issues, we tried to implement RankNet, which is a pairwise training strategy introduced by Bourget in 2005. So basically it is like a Siamese training. So for a given utterance, we take the channels 2 by 2. It doesn't, okay, it points like this. Okay, whatever. No, I went forward instead of pointing. Okay. So we have 2 pairs, we have 2 networks which are sharing the weights. So it's the same model. We take the output, the difference of the output of the network, and then we apply the binary cross entropy loss because RankNet, in RankNet, the labels are not the soft labels, but hard binary labels that just tell us which of the 2 channels is the best. Okay, so for example, in this case, if the best microphone is microphone 0, the model will learn to give a little bit higher score to the features coming from microphone 0 and a little bit lower score to the features coming from microphone 1. So this it's in the direction that we wanted to go. It's the line in which we wanted to go. However, there is still one aspect, one limitation. So here we are not taking into account the relative position between the pairs. So you can understand that swapping the last 2 microphones in the ranking, that is not a big deal. Actually, we don't care at all. The problem is when you swap the first microphone, maybe something in the middle. Okay. So the natural extension of RankNet is ListNet that was introduced by CAP in 2007. And in ListNet, all the channels for a given utterance are used together. So it's like list-wise training with respect to the pairwise training and the point-wise training, which was the first one, which I forgot to mention, sorry. So here, if we have M microphones, we have M networks with the same model shared weights as usual. We have the M outputs, and then we have the soft labels from the training set, again based on the word accuracy. And we can train the network using the cross entropy loss. Of course, we have to apply softmax to normalize the outputs of the network because we are using basically different networks for each channel. Okay, so given these 3 learning to rank strategies, we evaluated them on 2 datasets. A synthetic dataset generated with GPU rear. So you find all the details in the paper. We generated several different rooms, different microphone and speaker positions, reverberation times, and so on. Speech is taken from LibreSpeech, noises from pre-sound, and our ASR backend is the Caldi recipe for LibreSpeech. Then we also evaluated on the Chime6 data. I guess everybody here knows what the Chime6 dataset is. Anyway, it's dinner party recordings. There are 4 participants recorded by 6 Kinect devices distributed in the apartments. So overall, there are 24 microphones. And the SR backend that we use here is the system provided by the challenge organizers with the 2-pass decoding. Okay, very quickly through the model that we implemented is a temporal convolutional network based on computational. So there are 40 filter banks as input. The network takes a fixed length input, 2 seconds. And of course, the core of the architecture is the sequence of residual blocks with exponentially increasing dilation. So for the evaluation, we have, of course, our upper bound is the Oracle channel selection based on the word error rate. That is the best that we could do, and it is our target, which we will never achieve, of course. Then we consider another set of, let's say, Oracle methods based on the signal properties. So these are related to the state-of-the-art methods that I'm going to explain later. So here we have, these are Oracle methods because we compute the metrics representative of the quality of the signal, like STOI, PESQ, SNR, using the reference clean signal. So those metrics are correct. Okay, so if we pick the microphone based on the best STOI, that is the best STOI actually. It is not an estimation. And then, as a state-of-the-art method, we use the envelope variance by Wolf-Nadeau, which performs very well, chapter distance by Gerard Flores, and then the acoustic model entropy by Xiong that was used in CHIME 2018. Okay, so these are the results on the synthetic data. So in red, you see the upper bound, the Oracle based on the word error rate, the bottom part of the table. In the bottom part of the table, you have our MicRank learning to rank strategies. So you see that our approaches are better than the state-of-the-art, current state-of-the-art methods, so we improve over that. Also, the order of the learning to rank strategies is what we are expecting. So ListNet is the best one, and then followed by RankNet, and then the point-wise training. And an interesting result from this table is that you see ListNet is better than the signal-based Oracle methods. So, for example, the best one here is the like the STOI-based channel selection. So this confirms what we were assuming, that using information, trying to understand what is the DSR backend likes the most is actually giving an improvement with respect to selecting the best channel from some quality measures. Okay, these are the results on CHIME 6. So here, everything is a little bit complex because the task is very difficult, and of course the word error rate are pretty high. Anyway, you see, okay, you see in red the Oracle channel selection. So first of all, I mentioned at the beginning that picking the best microphone could give very good improvement, also with respect to channel to other speech enhancement approaches. So here, for example, you see that with respect to the CHIME 6 baseline, with respect to the CHIME 6 baseline, which use beamformit on a manually selected device, so there is a sort of human supervision, taking the best microphone, you get like 10 points improvement just doing that. So our methods here, we didn't report the point-wise because, it was worse, so we gave up. Performs better than the state-of-the-art channel selections. Performs better also than the CHIME 6 baseline, where the device is manually selected. It is not an Oracle selection, as one of the reviewers actually complained about that. It's pseudo-Oracle, but it is on human supervision, so it's not chosen randomly. A little bit disappointing here is that the STOI-based Oracle channel selection, here the STOI is computed using the closed talking signal, not the clean signal, because they're not available, performs better than our approach, than our methods. So here we look a little bit into that, and the main problem is the overlapping speech, which was not present in the synthetic data set. Here instead we have a lot of overlapping speech, in particular in the development set. Basically what happens is that when we have the two segments, when you have a segment with overlapping speech, the model could take the best channel for the other speaker, not for the target one. And in the current implementation, there's no way that we can handle that. So that's something that we have to figure out how to do it. And also the difference between RankNet and ListNet is a little bit, it's less. Actually, RankNet is better on the evaluation set. This is because the speech recognition doesn't perform very well, so the soft label that we use for the ListNet training using course entropy are rather flat. So the model takes, sometimes doesn't converge. And the hard labels here help a lot. Okay, so to conclude, I presented what we call MicRank, fully learned channel selection framework for distance speech recognition in ad-hoc microphone networks. Channel selection is formulated as a learning to rank problem, and the proposed method performs better than the current state of the art for channel selection. Open issue, future work. Of course, there's the problem related to the overlapping speech that I just mentioned a few minutes ago. And here what we would try to do is to try to provide some information about the speaker to the model, for example, appending some speaker embeddings or X vector to the acoustic features. Another thing that they didn't try, and I think it's very interesting, we should evaluate how sensitive the system is to using a different backend, with ASR backend, with respect to what has been used to compute the labels. So at least I think it could be an interesting analysis in terms of architecture and training strategy for the backend. Okay, so the code is available on the repository here managed by Samuele. Thank you very much for your attention, and if you have any question, let me know. I think, Richard, I will take the questions from the audience because you cannot see the audience.
Yes, I was going to suggest that. Are there people in the audience standing up and asking questions? I can't see that from here. First of all, before we proceed, let us thank Alessio and his co-authors for the presentation. We do have at least 2 or 3 comments from Takahiro Shinozaki and Carol Suchi. Are either of you here online? I don't see anything but ringing, but that's the way the interface is. Nothing, and we don't have. I don't see any questions about and the question stream related to this paper. There's still a bunch from the previous paper. So, Alessio, can you handle the questions from the room, if there are any?
Yes. Are there questions from the room? There are no questions from the room, I think.
Okay. So let me ask you. I thought that this was all very interesting to me. That you're getting very good results in channel selection for these ad hoc, widely distributed microphone arrays. If you were to take any of the approaches that you've looked at for close-spaced, geometrically distributed microphone arrays, like you might use for conventional beamforming, do you think you would get, or that you could get, results that would be comparable to what we currently see from beamforming, or is this are these approaches that are mainly for broadly distributed ad hoc networks where the traditional beamforming approach is based on geometry, knowing that you're not going to have spatial aliasing or more effective? What's your take on that?
Yeah, I think that, of course, it depends on how the beamforming or the channel combination is designed. Probably, I think it would be very similar if the beamformer is properly designed, because basically it's a weighted sum of the channels. So if the weights are, all of the weights are focused on one channel, then basically it's the same as picking that channel. So I don't think you will see a lot of improvement in that case. Probably beamformer would be a better choice. What you can do, if you have distributed devices, what we didn't do, actually we tried a little bit, but we didn't investigate in details. You can have, if you have multiple compact devices, like it is in Chime 6, because actually there are 24 microphones, but there are 6 microphone arrays, you can do local combination and then pick the best device afterwards. So you can try to combine both approaches.
Okay. Well,
there is a question from the audience, I think.
Yes, hello. Thank you for the presentation, and I would like to ask whether do you think that your solution is also applicable for selecting best microphone on a single device, meaning from microphone array? And I am thinking about the power performance increase. For example, if you have, the question is your ranking mechanism low power enough to select the best channel before, for example, keyword spotting, to save some power, instead of calculating keyword spotting on every channel and then selecting the best outputs?
Yes, I think so. This is similar to what I was saying before. So if you have a compact microphone array, probably if you just apply beamforming and VDRs, things like those, you will have very similar performance because you can assume, consider a case where the MVDR weights like weight 1 to the best channel and 0 to the other channels. So if you can combine, maybe you have more flexibility combining the microphones. But yes, in principle, yes, you can do that. What, for example, you could do something in the middle that we didn't try, but could make sense. So I said that decoding all the channels and then doing rover would be not possible, but maybe you can decode the top 5 and do rover on the top 5. So if you have a lot of microphones, you could select the top 5 microphones, apply MVDR to those, and then do your keyword spotting task. I think there's a question here from Sanjeev.
We're actually out of time.
Okay, I'll ask you later then. It's okay.
Okay.
Okay, let us thank Alessio.
No, there is a question from Sanjeev. There's a question from the audience.
Okay, Sanjeev, say it quickly because
yes,
we're in an overtime situation. We only have 5 papers in the session, so we can keep going. So go ahead, Sanjeev.
Okay. Yes, well, 1 minute, but we have one session left, so we have some buffer.
Okay, let me ask you. Sorry, Rich, you can't see me. I was willing to give up my question and ask it later, but Alessio says I can. I had a crazy idea, not a crazy idea. What you could do with Chime 6 is instead of using these Connect microphones, you could just rerun your whole experiment, but use the 8 ear-worn microphones of the people. And just see if it picks the microphone of the person who's speaking and how often it does that. And you might get a good sense of whether the method is doing what you intend, because there I think it's much more clear which is the correct microphone.
Yes, well, I mean, I'm not sure that the microphone, the speaker would be always the best one, because there could be some saturation or things like those.
Could be, yeah.
Okay, but yes, that could be a quick check, yes.
So it would be different from the simulated thing that you did.
Yes, yes. And there will be less overlap, of course.
Okay, and while you're there, one last online question from Yuri Vital. Did you use any data augmentation in training? And do you expect that the system will be stable for different acoustical environments? And with that, after that, we'll turn it over to the 5th talk for sure.
Yes. Now, yes, we did spec augment during training. And the other question I didn't understand very well.
Do you expect that the system will remain stable in different acoustical environments?
So ideally, so if we change so if there is a different acoustic environment not seen in training, so we don't know how the SR would behave, so that could be an interesting test that we didn't try, and I don't know, frankly. It depends probably on how much training material you have to train the model selection.
Okay, so let us thank Alessio Brutti and all of his co-authors, and we'll move on to the final talk. Thank you.